Okay, let's get started, folks. So this is lecture 12, and we're just starting the second half of the semester. I opened up a Moodle page for this week, and there's one packet of slides. It's this one here that's in front of you, and I'll use this one pack of slides for both today and Wednesday's class. I've got a number of movies showing some LED circuits that I've made, and they make this PowerPoint slide deck several hundred megabytes long. So if you do want to download this PowerPoint to see the movies, just be aware that it's several hundred meg long. If you want to see the movies without all that, putting all that data, all that memory on your computer, you could just re-examine this the Zoom recording of this lecture if you want. The PDF for this class is only about 10 megabytes, but that won't have the videos. Okay, so here's what we're going to do. I'm first going to show you our schedule going forward for the rest of the semester. And I've posted lab assignment number 3 to the Moodle site, and I'll tell you about that. And then we'll get into it, and I'm going to show you how to do lab assignment 3. And so sort of the big picture in terms of our schedule. Let's see here. Okay, here's the schedule, and I've got it in 2 forms. I've got it in this table form, also in a calendar form here. Kind of the big picture. You know, we're at the halfway point, kind of 12 lectures down and 12 to go. In my initial planning of the class, I had estimated that we would have about 8 lab assignments throughout the semester. It turns out we're going to have 5. We've had 2 so far, and we're going to have 3 going forward. And we'll cover all the things that I wanted to cover, but we're just doing it with a smaller set of labs. So just to sort of run down and give you a sense where they are, just looking at the assignments. So today I've assigned lab number 3, and it's to build a digital thermometer, which I'll tell you about. It's due in 2 weeks. So I'm keeping with the idea of giving you 2 weeks to do these things. And what I'm going to do for each lab is I'm going to devote an entire lecture just to Q&A associated with that lab. So I won't present any new material. This will be a week from Wednesday. So this week and next week we'll all be discussing the technologies, the techniques, the coding, the peripherals needed to do the lab. And then that square box there on Wednesday, the 30th, next Wednesday, the whole purpose of that class is just Q&A about the lab. If you have no questions, you don't need to come to class. If you have questions about the lab, come in and ask them. And the approach here is that as we get deeper into this, the circuits are going to get quite a bit more complicated. The coding won't be getting more complicated in terms of code. The embedded coding is relatively simple that we're working with, but we will be getting way down in the details of these different peripherals. A lot of different registers you have to keep track of and things like that. So it gets more technical, but not more complicated, really. And so the idea here is we want to, between me and the rest of the teaching team, we want to give you all of the help and assistance and resources you need to be able to do these. And so that's the idea behind devoting an entire lecture just to Q&A about the lab. Okay, so that one is to build a digital thermometer. And then in 2 weeks, I'll assign another lab that'll be due 2 weeks hence. The reason why that next one is due on a Monday instead of a Sunday is that Monday is a holiday. It's Patriots Day. We don't have class, so it's straightforward to give you the extra day to work on that. And I will have a Q&A day. So again, if you have no questions, concerns about the lab, don't even come to class. But that's just there for you to ask any questions that you have. And then our final lab will involve a sonar device and that little OLED display you have in your kit, and that'll be due on the very last day of class. And the second to last day of class will be Q&A associated with that lab. And then in between, it's me giving you information about the different components and peripherals and software concepts to do the labs. So that's the picture going forward. And I think you'll enjoy these labs. There's a fair bit of circuitry involved, so we want to make sure that you are comfortable with the basics by now. And I think based on the midterm, which, you know, the class as a group did very well on. So I think people are quite comfortable with the basics and prepared to go deeper into this stuff. But if not, if you are having some difficulty with the material from before the break, come see me or one of the TAs and make sure that you've got a working platform. You're able to compile. You got the make file figured out. You got all that stuff figured out, because you're going to be really needing to be very fluent in all that for the material going forward. Okay. The last point I want to make about this, and I'm going to do this by going to the previous slide here, all the same information, except I draw a line here. We're working with the Arduino Uno for the next 2 weeks, and that's with lab number 3. That's your little Arduino Uno board, and then we will put that board away, and we're just working with the bare Atmega chip on a breadboard. And so to make use of that, you need to have a voltage regulator, some capacitors, and some other things. And so there is an additional small bag of parts that I need you to pick up from the lab, and I'll tell you more about that in just a minute. So we're 2 more weeks on the Arduino, and then from there on out, we're just working with that bare chip on the breadboard and making use of some of the other devices that you have in your kit to bring that little chip to life. Okay, here's the lab assignment. It's build a digital thermometer that displays ambient temperature in Celsius or Fahrenheit. And the idea is there's a push button switch, and you push the switch down, it'll display in Celsius. You take your finger off the switch and it displays in Fahrenheit. One of the versions of this digital thermometer will display temperature on the serial monitor. You know, that's using the UART and sending the data out to your laptop display. And then another version of this will be, so these are going to be, you're going to do 2 complete builds, if you will, or you're going to build it once, and you're going to be reading temperature and sending that to your serial monitor via UART. And then you're going to, in a sense, tear it down and rebuild it, and you're going to be showing the temperature on this 4-digit 7-segment display. The idea of a 4-digit 7-segment display is that's the actual embedded system that you're going to build here. The first version of it, where you're writing to the serial monitor, that's just for debugging. It's how you check your code, check your temperature readings and conversions and things like that. And it's easier in many ways once you're writing things to the serial monitor. That's easier than writing to this 7-segment 4-digit display, as we'll see. So anyway, this is lab number 3. It'll be, there's a lot of wires in this, a lot of pieces to it. I want you to read the handout that I posted to Moodle. That has more details than I'm providing here. It tells you specifically the temperature range that it has to work over and how to display the information and things like that. Okay. Parts. You know, we had this snafu with the kits at the beginning of the semester where we had to build our own, and the last vestige of that is shown here. There is a small bag of parts that you need to pick up to complete the remaining 3 labs. It doesn't have many things in it. It's got a little temperature sensor that you need for lab number 3, and then it has a voltage regulator and some capacitors and a small motor, and those are for the later labs. And then there's also some alligator clip leads there that you should go pick up, and they'll just make it easier to make connections to the motor. So the lab that we're going to be doing right now, number 3, is the temperature digital thermometer. The next one is going to involve interfacing to a motor and varying the speed using what's called pulse width modulation. So it's a motor control lab. And then we'll do an ultrasound sensor. So stop by the lab during TA hours and pick up these 2 things, one of these pink bags and then one of these little packets of alligator clips. And the clips are just make it easier to connect to the motors, that's all. Okay, so what I want to do is walk you through most of the pieces that will enable you to do lab number 3. Okay, so again, the picture of that is you're going to build a digital thermometer. So obviously, you need to have a temperature sensor, and the temperature sensor is going to provide a voltage that's proportional to temperature, and we're going to have to sample that with an analog to digital converter, and that's something that we'll cover on Monday. So sort of the first half of this, or part of this system, is the part where you're sensing the temperature, and then really the more complicated part is when you're displaying the temperature. And so what I want to do with this class and part of next is show you how to do the display part of this. Okay, and so the way I want to do that, what I want to build with you here is this system shown here, where we've got our Atmega chip, and we're going to build a 4-digit ring counter. Now, you may remember that, or you should remember that from your logic design class. It's just going to count 0 up to 9,999 and then back to 0. So it's just a simple, an integer counter. 0, 1, 2, 3, 4, 5, 6, all the way up to 9999 and then back to 0. And this is just a simple counter that we can make with a loop. And all I want to do here is get that running on the microcontroller, and then have the current value, that 4-digit value, displayed both on the serial monitor and on this 4-digit 7-segment display. And as you'll see, there's quite a bit going on in getting it to work on that display. So the topics we're going to look at here. First, we're going to just review how do we send digits to the serial monitor via the UART. We covered that before break, but I know you took a break, and I suggested you take a break and put this down for a while. So we'll review that a little bit. And then after we review how we can send digits to the UART, we'll get into the topic of interfacing to LEDs. And first, we'll look at the little tiny LEDs, and then we'll go in and take a look at how you can interface to this thing that you have in your kit. Okay. All right. So how do we do it? Let's start. We want to we want to write a program that implements a 4-digit ring counter, just counting 0 to 9999 and then repeat. And we want to send the count to the serial monitor via the UART. So what we want showing up on your terminal window, on your laptop, or your PuTTY window if your Windows machine, you just want to see 0, 1, 2, 3, 4 on up through 9999 and then repeat. Okay. So I'm going to bring up on the next slide the codes that we left with last time when we were looking at the UART. Here they are. Okay, it's kind of a busy slide here, but I know you've got your laptops there in front of you to be able to see these things. So you recall, just to sort of remind you, when we talked about the UART, and it's going back a couple weeks because it was before the break and before the exam. But the idea was we wanted to make use of the UART to just send ASCII characters from the microcontroller via the USB cable to the computer when we're running to our host computer, and we are running a terminal emulator piece of software. So it emulates one of these 1970s era terminals, a dumb terminal, and it's just throwing characters up on the screen. And so take a look at the code on the left. All we did with this was we just wanted to send, well, actually, let's look at the description of what it does, right? This program continuously sends the letters wow with an exclamation point. It actually doesn't have an exclamation point. So it just sends the letters wow to the serial monitor via the UART. And take a look at the code here, right? I've got some functions in here that I wrote when I introduced the UART. The first thing we have is a user-defined function that we called UART init. What is that doing? It's initializing the UART. That's taken care of down here. And that does stuff like it enables the UART to transmit. It sets it up with 8 ASCII bits, no parity bits, 1 stop bit, and a baud rate of 9600 bits per second. All that is taken care of in this function down here. So when we just call UART init, this is a user-defined function. It's one that I wrote. Feel free to copy that verbatim into your code. That'll initialize the UART for us. Then we get into this while loop, and we've got send char W in single quotes. That'll come down here, and it'll just send the ASCII character W over, it'll transmit that via the UART. And once we've got a receiving terminal set up, in this case, it's going to be my laptop running a terminal window, we'll see that W show up on the screen. And then I send char O and then W, and then when I send char 10 and 13, that's going to do a carriage return, meaning it's going to bring the cursor all the way to the beginning of the line, then it'll go to a new line. If I don't do that, it'll just keep writing wow across the screen with no returns. So that's one way that we did this a couple weeks ago. I just wrote wow, right? And the idea was we were just sending a single character at a time. Then we made a little bit more elaborate version of the code where, and that's on the right, I still have those same functions. I've folded them up here using Visual Code Studio. You see I've sort of tucked the code. That's called code folding. I've just hidden it away so that we only see the name of the function and the details are hidden away, so we don't have to clutter up the screen with those. But I had this additional function that we don't have to get into now. You'll feel free to copy it and use it at will. And this was a function that allowed us to send a string of characters. And so here the example was, we created a character string, and I just gave the example, shall I compare thee to a summer's day? We initialized the UART, and then I called a function sendString, and I passed it that string. And what that function did is it took the string, it figured out how long it was, and then it sent each character one at a time. All right, this is basically the toolkit that we need for transmitting data via the UART. You can do things one character at a time, as shown on the left, or you can send things a string at a time, as shown on the right. Okay, and I'm showing you this because remember where we're going. We want to build a ring counter counting 0 to 0000 to 9999, and we just want to send those numbers to my serial monitor using this kind of code. Okay, so just to remind you, we're making use of these three user-defined functions, right? UART init, UART send, which sends one character at a time, or sendString, which would send a string of text. Okay, and we're always sending ASCII characters, and those ASCII characters are in codes that are defined here. This is only a subset of all of the ASCII codes, but the idea is every single ASCII character has associated with it a number. It can be in decimal or in hex, and that's the recognized standard for ASCII. So if we wanted to send wow with an exclamation point, we would send W, O, W, exclamation point. And we put each one in a single quote, okay, because that's how we send these. But I also wanted to show you, instead of sending W in a quote, let's take a look over here at the table, and you'll see that the ASCII character W, as a character in quotes, it's a W, but it also corresponds to the decimal number 87 or the hex number 57. So I could instead of sending W in single quotes, I could just send over the number 87, which is the decimal number that represents the character W. And then for O, that corresponds to the number 111, right? Let's pick that off the table. Lowercase o is 111. Okay, and then lowercase w is 113. I'm sorry, 119, that's over here. And then finally, we had our exclamation point, which was a decimal value 31. Now we could send these over as decimal. We could send them over as hexadecimal by putting a 0x in front of it. We send it over as binary if we want 0b, or we can send it over as a character in quotes. And the compiler is able to figure out the difference, because when the compiler sees a character in single quotes, it recognizes that as a character. If it sees a number without a prefix, it knows it's decimal. If it sees a number with a prefix 0x, it knows it's hexadecimal, and so forth, right? So these are two different ways. I could send over a wow exclamation point, or I could just use that third function and send the string wow. Okay, nothing new there, other than the idea that we could send these numbers instead of the characters. How could we send the letter G, right? And I just picked G at random here. But I want to show you 6 different ways of transmitting the letter G from your microcontroller via the UART to a to a serial monitor that's running terminal emulator code. So we could just use UART send G in quotes. Okay, let's go find G. G is represented by the decimal number 71 or the hex number 47. So I could also send 71. I could also send 0x47. Okay, I could also do this. UART send 6 plus 65. Well, why would I do that? Well, the only reason is 6 plus 65 is equal to 71. That's not too interesting. But what I wanted to show you is this sort of interesting way of doing it. If we, the character A in quotes is the same as the number 65. So, I mean, certainly at this point, this would make sense. UART send 71 makes sense. So UART send 6 plus 65 also makes sense. 6 plus 65 is just 71. You would wonder, why in the world would you send 6 plus 65? Why would you bother doing that? Well, we wouldn't, but we might do something like this. UART send 6 plus the letter A. That just means 6 letters after the letter A, B, C, D, E, F, G. Okay, so that's just 6 different ways of making use of ASCII representations to send these letters. Or you could send it as a string, and the string is in double quotes. So individual characters are in single quotes, strings are in double quotes. Okay, getting more focused to where we're going here, where we want to build this ring counter, and we're going to be sending over numbers. How do I send the number 4? 6 ways of doing it. I could just send the number 4. Okay, but let's go back and see where 4 is on the table. So 4 corresponds to decimal 52 or hex 34. So I could send 52, or I could send hex 34. Okay, but what's really sort of more useful here is this one here. I could send 4 plus the character 0. That's going to give me 4. And the reason why that's useful is we don't tend to have this table memorized. I certainly don't. And so I don't know off the top of my head what would be the character for the number 4. But one thing I can do is I can always write something like this: 4 plus character 0. And character 0 is actually the number 48, right? And the compiler will figure that out for me. So we'll be making use of some of this kind of stuff. And I realize you may be wondering, boy, why do we need all of this? This is sort of down in the weeds detail. But I just wanted to remind you, A, that we're sending these ASCII characters, and B, there are multiple ways of doing it. You can send them as individual strings, or you can do them as sequences of characters. And B, or in point C, you can represent them as characters in quotes or as numbers in decimal or hex. So I just got a question from someone in the chat. Asked me, so if you do UART send 4 plus quote 0, what does that get sent as? That is the same as quote 4, right? Quote in ASCII, quote 4 is the same as the number 4 plus quote 0. Okay, in ASCII. Okay, so in ASCII we're sending over characters, and so here 0 in quotes is the character 0. It's not the number 0; it's the character 0 because it has single quotes. Okay, so here's our ring counter, and I've got some pretty crude videos here that I just took with my phone. But let's show you the code here. I'm going to on the left here, the code builds a ring counter. So this code implements a 0 to 9999. It's a 4-digit ring counter, and it displays the count value on the monitor using the UART. And it's using this function ITOA, which is a function that comes with the C library. And what that does is it will convert an integer to a string. And not only that, you can specify the base that it works in. So let's take a look at the code here. All right, what are we doing? I've got, I'm initializing the UART, and then I have my while loop. That's my outer loop that will repeat in, infinite times. And then I have an inner loop, which is my ring counter. So it's a for loop going from 0 to 9999. That's what that for loop is doing. So it's going to go to 0. I is going to go to 0, 9,999. We'll exit the for loop, but then the while loop will cause it to repeat. So that's how I've implemented a continuously repeating ring counter, a for loop inside a while loop. And there are lots of ways of doing this, but this is just one way of doing it. So the value of the ring counter is the number I. And I'm calling it an unsigned integer because it's only positive. I could get away with calling it just an int, and it would be a signed int. But as a programming practice, when I'm dealing with something that's only going to have positive values, I'll give it the data type unsigned int. Okay, and so here's the function here that's important: itoa. I, my string 10. What I've done here is I've created a variable called my string, which is an array of 10 characters. And this function, itoa I, my string, will take the number I, it will convert it into a string, and it'll store it in my string. And it'll store it as a number in base 10. Okay, and you could also have it actually change that to a 2, and it would take I and it would store it as a bit pattern, 1s and 0s, but as characters. And this is why I asked you not to use this function on lab assignment number 1 at the beginning of the semester. So once we've taken the number, right, I is an integer here. It's not a character, it's an integer. And we want to send ASCII characters. So itoa converts that int to a character string. And then we just send the string over using the function myString down here, right? And by the way, when you want to make use of these functions, what you do is you just write them once and then copy them to the bottom of your code. Every time you want to use them in your programs, just take those functions and cut and paste them in there. Some people like to put these definitions of these functions up at the top of the code. I prefer to put it down at the bottom. That way I keep the main function sort of front and center, or keep that up top. In order to do that, you have to have what's called these function prototypes up here, so that the compiler knows, it says, okay, there's going to be a function that I'm going to get to. It's called UART init, and it's going to be defined somewhere else, right? So this is the way I always format my code. Okay, let's just go and run. Well, let's look at 2 different ways of running it. So on the right side of the screen, this is the result of that. If I download that and let it run, it's just counting, right? And you can see it goes, it's kind of blurry here, but 4, 5, 6, 7, 8, and so forth. And it would just keep on scrolling. And the reason why, you've got what it's doing is it's printing one number, the next number, the next number. And I have a carriage return and a line feed after each one. So it prints a 4, the carriage return moves the cursor over to the beginning of the line feed goes down to the next line. So that's what you start send 13, that's the ASCII character for a carriage return. And when you send a 10, that's the ASCII character for a new line. Now, what would happen if I took those out? So I'm going to show you on the far right, I'm just going to show you a little movie here, and all you're going to do is just stare at that number right there. But I'm going to show you what happens if I comment out the carriage return, or I carriage out the, I comment out the line feed. So let me go and run this. It's a short little movie, but here. 16, 17, 18, 19, okay, 20. So all I've done is I've just commented out that line feed, and thereby allowing it to always retrace the number on the same line that it's been on. So these are just 2 different ways of displaying numbers like this to the serial monitor. And here I'm using a terminal window on my Mac, but on your Windows machine, you would be running PuTTY, and you'd be opening up a terminal on PuTTY and seeing this kind of a display. Now, why do you do this? as I've emphasized before, the vast majority of 8-bit embedded applications do not have a monitor hanging on them, right? They're headless. They don't have all that. But you use this for debugging purposes. And this is, you'll find it to be very handy when you're trying to figure out, is something working and you don't have a display. You just want to show a number on a display. You don't have it. Do what we're doing here. Once you get these three UART functions, sort of, once you get comfortable with those, you'll find it to be very straightforward. When you need to debug something, you can just send the information out to a serial monitor and see the numbers there and say, okay, does this make sense? So you'll use it as a debugging aid. Okay, so let me just show you one more way of doing the same thing. And the reason why I'm doing this is I wanted to get a display that would actually show all 4 digits of the ring counter, including the leading zeros, okay? And so here's a different piece of code, all right? This code implements a 0 to 999 ring counter and displays the count value on the monitor using the UART, and it sends each count digit individually. So here, instead of sending them all as a string, I'm taking that 4-bit number and I'm unpacking that. I'm finding the thousands place, that is the most significant digit, and I'm transmitting that. And then I get the hundreds place and transmit that. The tens place, transmit that. The ones place, transmit that. And then I do my carriage return and line feed. So look at this is how we do it, right? A digit is equal to our count divided by 1,000. Now, this is integer division here. So let's assume, for example, that I have a count 6789, right? If I divide that by 1,000, well, 6789 divided by 1,000 is 6.789 if I were using floating point. But since I'm dealing with integers, 6789 divided by 1,000 is 6. Okay, so when you do integer division by 1,000, you just get that thousands place. And the rest of the mathemagic here, similar to what you did in lab assignment number 1, I'm using a combination of integer and modulo division to just pull apart the thousands place, the hundreds place, the tens place, and the ones place, and send them all over, and there's the result. Okay, so I've just showed you 2 different ways that you could send that digital count over to the serial monitor. And so this is, like I said, for debugging. Now, in your lab assignment, what you're going to be doing is you're going to be taking a reading from a temperature sensor, which, by the way, you don't have in your kit yet. It's in that little pink bag you have to go pick up in the lab. But there's a temperature sensor. It's got 3 wires on it. It's got 5 volts ground and then a voltage. And you'll configure the analog to digital converter. You'll read that voltage, and then you'll just send it over to the serial monitor. So, well, that's basically it. You have to figure out conversions between Fahrenheit and Celsius and things like that. But the real application is not sending a 4-bit display to the serial monitor, but it's making it show up on an LED display. So now that we've reviewed this, I want to now talk to you about LEDs and show you the proper way of hooking up LEDs. Before I do that, let me pause and see if there are any questions about any of this serial monitor UART stuff. Anything? Okay. So now let's talk about LEDs. Okay. So I want to talk about how to interface and program LEDs. So, and when I say interfacing, I'm really talking about the wiring. And the point here is that you want to use current limiting resistors. If so far you've been hooking up your LEDs to your Arduino board without using resistors, you've been doing a low-key version of what I'm going to call engineering malpractice, and I'll tell you why I call it that. I want to show you the proper way of hooking up LEDs so that you don't burn them out. And we're going to talk about a physiological effect called retinal persistence. And this is the basis behind all of these multi-digit displays that you see. Very interesting effect. Then we'll get into actually how to program the 4-digit LED display that you have, how to hook it up and how to program it. Okay, so our LEDs. So, you know, the heart of this assignment is this 4-digit 7-segment display, and each of those digits looks like this. And it, you know, it has the 7 segments: 1, 2, 3, 4, 5, 6, 7, and it also has a decimal point here, DP. And it's funny, they call it a 7-segment display plus decimal point. They don't call it an 8-segment, they call it a 7-segment display. And so just by turning, and what's inside each of these is just a bunch of LEDs. You know, this is the symbol for an LED. And, you know, we've been using these in our circuits so far. But each of these segments is just an LED. It's just shaped rectangular. And by illuminating preferentially some LEDs versus others, you can cause different patterns to show. And I'm showing all the digits between 0 and 9. You could also activate the decimal point. You could also do letters. You can make an F, you can make a C, you can make, you know, between uppercase and lowercase, you can do a variety of letters as well. So we want to get to how to do all of that. But I want to just start out with the real basics here. What's the proper way to hook up an LED? And here I'm referring to the LEDs that you have in your kits. So you have a handful of red LEDs, you have a handful of green LEDs, and you have one RGB LED that's red, green, and blue all in one package. And then you have this 4-digit 7-segment LED. And the circuit the basics behind the circuit for all of them are the same. The key idea here, well, first of all, let me just tell you that each of these the LEDs in your kit, the red ones and the green ones, have a long wire and a short wire. The long wire is the anode and the short wire is the cathode. And in terms of the circuit, the schematic symbol for an LED, it looks like an arrow, right? This is actually the schematic symbol for a diode. And in our case, we're using light emitting diodes. But you see it's an arrow and it's pointing downward. That's the idea. Current only flows from the anode to the cathode in a diode. So these are examples of electronic devices. They're made out of semiconductors, and current really only flows in one direction. That's why it's an arrow. So it's important to get the polarity right. There's the anode is the long lead. That has the positive polarity applied to it. And the cathode is the short lead that has the negative polarity, so that current will flow down through the device. Okay. Now, the idea is that the brightness that you're going to get, the luminous intensity, how bright this thing is going to be, is proportional to current. So if you if you have a certain current that goes through it, you're going to have a certain brightness. And we're not going to worry about the dimensions of the brightness. They're often measured in millicandelas, which are millionths of a candle, but we're not going to get into that. But the point is, the more current that you have going through it, the brighter it's going to be. But here's the important thing. For essentially all of the diodes that we have in our kit, they have a forward voltage across them of about 2 volts, approximately 2 volts. Can be a little more, can be a little less, but you can't go wrong by using 2 volts. That means when it's hooked up in a circuit with a battery and a resistor, you're going to have a voltage drop of 2 volts from the anode to the cathode. And these diodes will work with a maximum forward current of 30 milliamps. That's according to the manufacturer's specification. You can get that from the data sheet. So that means that you can put more and more current into these things, and they'll get brighter and brighter. If you go above 30 milliamps, according to the manufacturer, you're going to damage the device. You're going to shorten its lifetime. And I'm going to show you some examples of that. So if you want to know a whole lot more about this, you can go to this link, right? That's my e-textbook that I wrote for a different class, but that has a whole chapter on diodes. So if you're interested in this in more detail than we're covering, go take a look at it there. But I'm just going to show you next, take the information on this slide, and I want to embed that in a little basic circuit analysis that you saw last semester already in your circuits class. So first of all, you will always use a current limiting resistor to drive an LED. If you don't have a current limiting resistor driving the LED, that's really engineering malpractice, and I'll show you why. Okay, we're working with 5 volts. I say 5 volts because the pins the pins associated with our Arduino are 5-volt pins, and there's a 5-volt output from our Arduino. So when we're hooking up LEDs, we're working with a 5-volt supply. So look at this little circuit. You've got your 5-volt battery, you've got a current limiting resistor, and you've got your LED. And I just want to show you how a resistor is used to limit the amount of current that flows through the LED. And so remember from circuits that you can use Kirchhoff's voltage law to write the sum of the voltages around that closed loop. And so we're going to do that to analyze that circuit. And that's right here. I have -5 plus the voltage drop across the resistor, V sub X, plus the voltage drop across the diode, V sub D equals 0. So that's just KVL, Kirchhoff's voltage law, which you learned about in circuits. This resistor, it's going to have a current I sub D flowing through it. See that there's I sub D is the current through the LED, but it's only one loop in this circuit. So I sub D is the current flowing through the whole circuit. And the big picture, the idea here is by choosing different values R sub X, we can set the appropriate current I sub D. Small resistor, you're going to have a small current. Small resistor, you have a high current, and big resistor, you have a low current. Continuing with this analysis, though, from that first line to this next line, I'm just using Ohm's law. The voltage drop across the resistor is just the resistance times the current through it. And then in this next line here, I'm just making use of the fact that the voltage drop across the diode is 2 volts. That comes from the manufacturer's data sheet. It's called the forward voltage drop across the LED. That actually varies from one color diode to the other, depending on the semiconductors that are used to make them. But 2 volts is a reasonable enough approximation for what we're doing here. So you can take this equation and you can solve for the current through all the elements in the circuit as a function of the resistance. So if I choose 3 different values, 100 ohms, I'm going to get 30 milliamps. Okay, and there's an example. If I choose 1 kiloohm, I'll get 3 milliamps. All right, and maybe it's a little less bright. And if I choose 10 kiloohms, I'll get 0.3 amps, and it looks less bright. Now, how bright these things are, it really depends so much on the ambient situation. I took pictures of these. I'm going to show you some movies of these. They will appear to be bright or dim, depending very much on the ambient lighting. You take them outside on a sunny day, and you can barely see them, even when they're running very strong. Okay. In your kits, most of you have 1,000 ohm resistors, 1K resistors, and so that you get this kind of a glow out of them. In some of the kits, we were building them, and we ran out of 1K resistors, and so we went with 100 ohm resistors. And so if you use those, you'll get a bit brighter glow. It'll still be within the spec. By the way, if you want to come in and get more resistors, come into the lab and get them. We've got thousands of them. If you want to know how can you measure, or how do you determine the resistance of a resistor you have, they have a color code on them. You can look up the resistor color code and just use those color codes to figure out the resistance, or you can use a multimeter to measure the resistance. If you want a multimeter, come in and get one, pick it up in the lab. It's yours to keep. Your engineering fee paid for. They're inexpensive little $10 pocket multimeters, but you come and get one if you want one in the lab. Okay, what happens if we do this without a resistor, right? If we build this circuit here. So in other words, I have a diode that wants to have a 2-volt voltage drop across it. And I connect that in parallel with a 5-volt battery. I've got 5 volts in parallel with 2 volts. Obviously, that's going to be a problem. The way to analyze that circuit would be to take the previous circuit that we had and let R go to 0. So if we have this equation, we had that the current was 3 divided by the resistance. If you take the limit, R goes to 0, I is going to go to infinity. So if you build this circuit and you hook it up without any resistance, then you're going to have, theoretically, you'd have infinite current. Now, power supplies cannot deliver infinite current. No power supply can. So what in fact would happen is the actual current that you get through your LED would be limited by a variety of things. It's going to be the maximum current from the power supply, or small resistance in the power supply, or small resistance in the wires. But in either case, you're going to damage the LED. And that's why I say I consider it to be engineering malpractice for if you were to ever build a circuit that that had an LED but didn't have a resistor. Now, if you're lucky, now this is a strange thing I'm about to say, but if you actually hooked up an LED to a battery or a 5-volt signal without a resistor, and it was damaged and it blew up, and you could see that it was blown up. It looks like this one here, right? See how it's damaged? You can actually see that black mark in the middle of it, right? You're fortunate to get that, because that means you can look at it and you can say, this LED is blown out. I hooked it up, it supernovaed, it glowed briefly, and then it burned out, and here it is. I can see the evidence that it's blown out. More often than not, they're damaged, but they don't have that obvious indication. And I'll show you that on the next slide. Here, I've taken 4 LEDs, and I've hooked them up to the 5-volt supply on my Arduino. So here what I've done is I've taken the 5 volts and ground from here, brought those out to the breadboard, and I've set up a 5-volt rail on the top of the breadboard, a ground rail on the bottom. Red wires are always used when you're connecting directly to your VCC, your 5-volt rail. You use a black wire for ground. And then I just chose, 4 different resistances. I chose 100 ohms, 1 kilo ohm, 10K, and 0 ohms. So on this last one on the right, what I did is I hooked up the LED, the anode, directly to 5 volts. Now, the Arduino Uno is only capable of giving us 200 milliamps out of the 5-volt pin. So I'm pulling about 35 amps from all of those other LEDs. So what that means is that I'm subjecting this LED on the right to about 165 milliamps. It's hooked up directly to 5 volts, but that 5-volt pin will not produce more than 200 milliamps. So I'm really abusing that LED on the right with about 165 milliamps. The manufacturer spec says don't go above 30. I'm doing it anyway. This is, I'm just going to show you the next slide where I shut off the lights in the room. Okay, everything looks much brighter, right? All right, so they all look fine. All those LEDs are happy. None of them are unhappy, right? Well, I'm going to show you a movie next. And let's see if it's on this slide. And I want you to keep an eye on this LED on the right. Okay, here's the movie here. Just keep an eye on that one. Now here, they're all just hooked up to 5 volts. So what's happened is I've been running it for a while, and it's overheating and it's getting damaged. It's not obviously burned out because it's on sometimes and it's off other times. Now, just imagine if you or someone else took an LED, powered it up like this, damaged it, and then put that back into the parts bin. Okay, that's why I call this engineering malpractice, and I say that because the manufacturer spec says don't put more than 30 milliamps through it, but it takes time to get a resistor, get the right resistance, put it in there. It's easier to just skip it, right? Well, let me show you what happens if I take this LED. It's not blown, it's on sometimes, and I hook it up in another circuit. Here it is right here. It's that same damaged LED, and I'm just hooking it up to 5 volts, and I put a resistor on there now, all right? And suppose that I went into my parts bin and I took this out, all right? It's flickering. Now, suppose I'm trying to debug a circuit, and the circuit is supposed to blink an LED. And I got a blinking LED, right? What you don't want is to not be able to trust the darn LED, right? But this is a case where it's been damaged, but it's not been damaged so much that it's burned out. It's damaged in such a way that it's blinking intermittently, right? And you'd hate to actually pull that thing out of a drawer, stick that into a circuit, and use that to try to diagnose some problem that you could have in software or hardware and wiring, okay? So, and I spent a long time on this. I just wanted to make the point that you want to take a look at the data sheet, get the information on the maximum current, and then use those current limiting resistors. Okay, so that's that. Now, let's go ahead and sort of do some stuff with LEDs here, okay? Here I just want to show you an 8-bit binary counter. So I've just taken 8 LEDs, and I've hooked them all up to port D pins of my Arduino Uno. So this would be, port D corresponds to pins 1 through 7. So each of those wires goes to one of the pins of the Arduino Uno. Then they go into some resistors. I have 100 ohm resistors here, and then they go into the LEDs. And here's the code I'm going to run. Okay, and this is just a counter. Well, let's go through and take a look. First of all, I wanted to make a point about this first line in the code. If you look in your textbook, the author always has this line in the textbook, in every example code that has that. And we haven't had that in any of our code. So what's that all about? Well, the microcontroller, it doesn't have its own sense of time, right? It doesn't know what time it is. All it does is it counts the number of times it's doing something. So it might do something 100 times, it might do it 1,000 times, it might do it 1,000,000 times, right? But all it knows is the number of clock cycles that have elapsed, but it doesn't know the duration of a clock cycle. So you have to tell it the frequency of your clock. And so you can do it two ways. You have to actually define FCPU, right? It's a symbolic constant, like other times when we do a define statement, but the compiler needs to know that. And that gets used by the delay function. It gets used in lots of places, but it gets used in particular by the delay function, because when you have a delay of 100 milliseconds, what that function is going to do is it's going to be based on 100 milliseconds is going to be based on a certain number of clock cycles at a certain clock frequency. So you have to tell it the clock frequency. We always tell it that frequency in our makefile. If you look in the makefile, if you look sort of deep in there, you'll see a line that says -D, that means define, FCPU 16 million. That's the line where we're actually defining this. So you can either put it in the makefile, which is where we're putting it, or you can put it in there as a defined statement. I just wanted to call that out for you, just so you'd be aware of that discrepancy between what you see in the textbook and what we see in our code. All right, what's happening with this code? So I declare an unsigned character, I, that's equal to 0. I set all the pins of port D as output pins. I have my while loop. All right, I'm just incrementing I. So I goes from 0 to 1 to 2 to 3 to 4 to 5 to 6, right? All the way up. I is data type unsigned char. That means it's an 8-bit unsigned integer. It goes from 0 to 255. And so what will happen is every time I go through the while loop, I start at 0, 1, 2, 3, 4, and then 250, 251, 252, 253, 254, 255, and then it rolls back to 0. So this is an 8-bit ring counter here. I don't have to reset I. It'll just reset from 255 to 0. But what I'm doing is I'm just letting port D equal I. So I'm taking a number between 0 and 255, and I'm just assigning that to port D. So 0 is just going to be all zeros. 255 is going to be all ones. And everything in between is the corresponding bit pattern in between. So when I run it, you'll just see this code that's just counting those LED digits in time. So it's the least significant bit on the right, most significant bit on the left. And I'm just counting from 0 to 255 in binary here. and I stop it once it reaches the top. Okay, so I just wanted to show you one way that you can use a series of LEDs to convey the value of a number. So you can put a bunch of LEDs out there to show the binary representation of a number. We can also send it out to the UART, but now I want to show you. First, I want to show you the RGB LED, and then I'm going to show you how we program these seven segment displays. Okay, just one more variation of the LED is the RGB LED. That's the red, green, blue LED. You have one of these in your kit, and so it's you have what's called a common cathode LED, and so you see the schematic. It's actually 3 LEDs all combined into one plastic dome, one package, and so it has one long lead, and that's the common anode. And then it has the 3. The one long lead is the common cathode, and then it has the 3 shorter leads, which are the anodes, the plus side for red, green, and blue. And then here's the schematic for it. And so if you were to hook that up, each of those anodes needs its own resistor, right? You could then ground the common cathode, and you could run voltage across it and get it to glow. Now, what's interesting about these RGB LEDs is, if you take it and you shine it on the wall, you could get your red, your green, and your blue. And you may know already that if you simultaneously illuminate an area with blue and green, you'll actually get cyan. Your eyes will see the superposition of those. This is called additive color combining. Your eyes will perceive that superposition, position of red and of blue and green as cyan color. Likewise, if you take the blue and red and you shine them both on a wall, you'll see magenta, right? If you take the green and red and shine them both together on the wall at the same time, you'll see yellow, and all of them together, you'll get white. And this is the basis for all these multicolored light strips that you see all over the place. And so let me just show you a little bit about that. Okay. So I got a whole bunch of different things on this slide. So let's take a look at this one up on top. This is just walking through the colors, not quite the colors of the rainbow, but I'm just activating the red, the green, the blue, and then the combinations of those in sequence. So I just have a little LED, and I just popped it inside a little pill container. The reason why is what you want to do is sort of diffuse the light. Otherwise, you'll tend to see sort of a narrow beam of light, red, green, and blue coming out. But when you put a sort of a semi-opaque light diffuser over it, it kind of blends all the lights together. So let me just show you this little movie here. And you can see it just sequencing through the different colors. And all I'm doing is I'm doing, red and then green and red plus green. I'm combining all those colors together. Okay. This one on the right, I happened to be in Amsterdam when I saw that. And I was teaching another class, and I wanted to illustrate how, if you look on the far left, if you take blue and red and you illuminate them together, you'll get magenta. And it was just such a good example of magenta color that I captured that one as a picture. Okay, just some other things that we do with lights over in the far left. These are some students that I had in my electronics class for mechanical industrial engineers a while ago, and they were interested in making earrings and jewelry using RGB lighting. And so that was just sort of a weekend activity, and they were intrigued by this idea of color combinations. And then on the right, I teach a class with Jenny Beeman. Jenny is the director of our Stonewall Center on campus, and we call the class Queer Lights. And it's a class that, from the get-go, seeks to combine technology with learning about the experiences of queer people in one class. And so we talk about sort of the meaning behind different pride flags, and then the students spend a whole semester making a light-up project that typically has some semblance to one of the pride flags, like this necklace that was shown here. So those are just some examples of different things that are done with these RGB LEDs. We're going to make use of the RGB LED that you have in your kit in lab number 4, where we're doing some things with measuring light in the room and then responding to that with some different color patterns. So we'll get to that in lab number 4. Okay. The next topic here is this common cathode 4-segment LED. And what I'm going to do is I'm going to end the class here, and we'll pick it up on Monday, and we'll cover this component from start to finish on Wednesday when we come back. Okay. So it's the same slide that you have here. You can go through them if you want to beforehand, but we'll show you really how to get in and code up one of these things, taking advantage of the retinal persistence of vision effect. Okay, so we'll leave it at that. If you have any questions or comments, I'm happy to take them. Otherwise,
questions in the room.
You've got questions?
I do not see any questions in the room.
Okay, well, we'll just we'll call it a day then.